This video will go over Chapter 1, Section 1.4 and Section 1.5 on significant figures, just Part A of Section 1.5. So let's start with measurements. So every measurement is composed of a number and a unit. And it is very important that whenever you give a measurement, you give a number and its unit, because the number is meaningless without its unit. For example, if you were reporting the proper aspirin dosage and we're saying 325 and you don't say the unit, then we are left to wonder, is it 325 milligrams or 325 grams or micrograms or pound? And for example, if it's the proper aspirin dosage for a patient in an hospital, then this can have dramatic consequences if you are giving the wrong dosage. So it is very important that you write down the unit of your measurement. Another example to make you understand the importance of this, if you are reporting a fast time for the 100-meter dash is 10. And so you're saying it's a fast time, but if you don't specify the unit, if it's 10 hours or even 10 days, then it would not be a fast time. But if it's 10 seconds, then yes, it's a fast time. So it's all relative, right? The unit gives you the standard quantity to compare your measurement to. So you need that to understand really the value of your measurement. So there is the metric system and the English system. And in science, we use the metric system. Each type of measurement has a base unit in the metric system, and the quantity, if the quantity is length, the base unit in the metric system is the meter, and the symbol is lowercase m. For quantity of mass, the base unit in the metric system is the gram, and symbol is lowercase g. For volume, the base unit is the liter and the symbol is capital L. For a quantity of time, the base unit in the metric system is the second and the symbol is a lowercase s. So it's important you recognize what quantity those units measure, because if you see a measurement with those symbols, you need to understand that they are measuring length if it's meter, and mass if it's grams, and volume if it's liters, etc. So in the metric system, prefixed units are related to the base unit by a power of 10. So using prefixes, the metric system has many different kind of units that are related to each other by power of 10. So there are the prefixes that will increase the size of the standard unit or the base unit, like the kilo, mega, and giga will increase the size of your basic unit. The kilo will increase it to 1,000 times the size of the basic unit. Mega is 10 to the 6 in scientific notation. And giga 10 to the 9 in scientific notation. And then from deci, centi, milli, micro, and nano, these prefixes are making the base unit smaller. The deci is 1/10 of the base unit. The centi is 1/100th of the base unit. Milli is 1/1000th of the base unit. Micro, 1/1,000,000th of the base unit. Nano, it's 1/1,000,000,000th of the base unit. So notice the symbols. here I want to emphasize micro. That symbol is Greek letter, the micro, for micro, mu. Notice here our milli has for symbols lowercase m, which is the same as meter. So milli, you will recognize it because it will be in front of the base unit. So if you have two m, the first m will mean milli and the second m will mean meter. So let's look at these units. So how can we use that table? By the way, this is in the reference for Unit 1 in your Canvas module for Chapter 1. There is a link to a file where you have the table like this that you can use as a reference. So when we are measuring length, the base unit is the meter in the metric system. And so to learn how to use those prefixes, if you want to write the equivalence between, for example, 1 kilometer and what it is in meters, you will write 1 kilometer, so K for kilo, M for meter. And so 1 km, 1 kilometer, is equal. And then you change the prefix by its value. And kilo has a value of 1,000. So you change kilo by 1,000 and you rewrite the base unit, which is meter here. And so that there you go, you have this equivalence that says 1 kilometer equals 1,000 meters. Same thing with millimeters, for example. 1 millimeter, as I said earlier, the first M is the milli, the second M is the meters. 1 millimeter. If you change the value of the milli, if you put the value of the milli prefix, it's 0.001 meter. So you have then your equality that says 1 millimeter is 0.001 meter. And the centimeter is another unit used a lot in science. 1 centimeter. Centi is the prefix. If you change its symbol by its value, centi has a value of 0.01. So 1 centimeter is 0.01 meter. So to be able to write down these equalities, you need the table that was in the previous slide, or you need the file I told you about, the reference for Unit 1 in Canvas. Because you need to be able to write those equalities. So if you're measuring mass, first, let's say that it's a measure of the amount of matter in an object. So it really measures the amount of matter. And it's not to be confused with weight. Weight is a force that matters feels due to gravity, which means that wherever you are in the universe, the mass of an object will be the same. However, the weight will be different. For example, if the weight of a person is 100 pounds on Earth, now if you place that person on the surface of the moon, where the gravity is much less, then the weight will be less, much less, because the gravity is less. So weight is force depending on the gravity, while mass is really measuring the amount of matter in an object and doesn't change upon location. So in the metric system, the base unit of mass is the gram, lowercase g. And so again, if we use a prefix like the kilo, we can write that 1 kilogram. And so in symbol, it's kg, 1 kg. And now if you change the symbol kilo by its value, a kilo as a value of 1,000. So you remove the K and write 1,000, and you rewrite the base unit, the gram. And so you come up with 1 kilogram equals 1,000 grams. Again, with milligram, it's the same. 1 milligram, symbol is 1 mg, m for milli, g for gram. If you change milli by its value, the value of the milli prefix is 0.001, and then you bring back the base unit, which is gram in this case. So then you come with this equality that says 1 milligram equals 0.001 gram. So these are, you know, the gram is a unit of mass. You need to recognize whenever you're given grams, that's its mass. The base unit for the volume is the liter in the metric system. Liter has the symbol of capital L. Again, 1 kiloliter is 1,000 liters. If you replace kilo by its value, which is 1,000, you get 1 kiloliter equals 1,000 liters. Another unit that we will use a lot is the milliliter. 1 milliliter, so lowercase m, capital capital letter L. 1 ml is, so you replace milli by its value, 0.001 liters. Notice that you can rewrite these equalities by saying that, so let's say you multiply the left side of the equality that says 1 milliliter equals 0.001 liter. If you multiply the left side by 1,000 and you multiply the right side by 1,000, so on the left we will have 1,000 milliliters, and on the right we will have 0.001 times 1,000, it will be equal to 1. And so this equality can be written as 1,000 milliliters equal 1 liter. And that's the same equality, right? Because you multiplied by 1,000 on both sides of the equality. So it doesn't change the equality, it still holds. And so this can also be written like that. Volume can be measured by measuring the length times the width times the height of a rectangular object. And so if you take the length in centimeters times the width in centimeters times the height in centimeters, the unit of the volume in this case will be expressed as cubic centimeters, because you can multiply the centimeters together. And here they're multiplied 3 times. So then it's cubed. So cubic centimeters is a unit of volume. And so one equality that is very important and useful in the metric system is that the milliliter is equal to 1 cubic centimeter. So if you imagine 1 centimeter by 1 centimeter by 1 centimeter, that small volume of a cubic centimeter is equal to a milliliter. And so this is used a lot in medicine, for example, but in medicine, to make it easier or more clear maybe, they use the cc, 1 cc, and cc means cubic centimeters. The first C is for cubic, the second is for centimeters. 1 cc is equal to 1 milliliter. So this is an important equality. Again, this is also in your reference of Unit 1. So because we live in the United States here, there is also the English system that is used in everyday life. So we need to have all these equalities that change units of the English system between other English system units. And also we need the metric to English systems equalities. So if you look at this table, the first column indicates what kind of quantity we are looking at. The second column tells you English unit equalities that allows you to change unit, one kind of unit to another kind in the English system only. And then the third column tells you how you can change a unit from the metric system into a unit from the English system. So you want to, when you need to find an equality, you want to first look at the quantity. What type of quantity? Is it a length, a mass, or a volume you're dealing with? And then is the question asking to change an English system unit to another English system unit, or is it between the metric system and the English system? And so you want to look at the proper or appropriate column whenever you need that. So you can look at this. This is provided in the reference for Unit 1 in your Chapter 1 module in Canvas. So make sure you have this in hand, and the best would be to print that reference for Unit 1 and have these available. So let's do a learning check now. And again, when we do a learning check, I advise you to stop or pause, rather pause the video and do the problem on your own and then check the answer. Because if you only follow and hear the answer before you have thought about it yourself, you will not learn. It is important that you try to do this on your own first. So for each of the following, indicate whether the unit describes a length, a mass, or a volume. If we are talking about a bag of onions of 2.6 kilograms, what is this? So kilograms is a unit of mass, so that's mass. A person is 2 meters tall, 2.0 meters tall. Tall refers to height. Height is a unit of length, and meters confirms that it's a length. The medication contains 0.50 grams of aspirin. So aspirin is in a tablet form. Here we have grams. When we have grams, we should think about mass. Grams are units of mass. A bottle contains 1.5 liters of water. Liters are the unit here, and that's a unit of volume. So you want to know by heart that liters are units of volume, grams units of mass, meters unit of length, and etc. This is important to recognize what kind of measurement you have. So this is not in the textbook, but we need to know how to make measurements with correct precision. And this is very much needed for the first lab. So numbers are obtained when you measure a quantity such as your height, your mass, a mass, or a temperature. Here we will try to measure a volume. For example, if we had graduated cylinders like what we have in the picture here. This is an image of a graduated cylinder with a liquid in it. And so when you are trying to obtain a measurement from something like that, you want to observe the numerical values of the marked lines. And then, so you will know for certain that your measurement is between two values that are known because there is a line for these. And then you need to estimate the value of the number between the marks. That's that's what is maybe the most difficult, is to estimate one more digit between the marks. So in this example here of a volume, we see we start on the bottom from 20 to 30, 40, 50. It's probably milliliters here. And so the liquid here, when you have a liquid, you want to read the liquid in a narrow container. You want to read it at the bottom of the meniscus. The meniscus is the curve that you see at the surface of the liquid, and typically it curves downward. And so you want to measure at the bottom of the meniscus, right? Where it shows here meniscus, where you have the dashed line is where you want to read this measurement of volume. And so from 30, I can move to in between 30 and 40 to 35, because we have 1, 2, 3, 4, 5 lines up to 35. So we have 35, and then 36 is another line, shorter line, right under the meniscus, right? So we know for sure we have 36 milliliters here, and the line that is above the bottom of the meniscus, slightly above, is 37. So we know for sure our volume is between 36 milliliters and 37. And now we need to estimate where the dashed line is falling between 36 and 37 milliliters. And here, honestly, I would think that this is in the middle. So then I would say it's 36.5. So that would be the way I would read this measurement, 36.5. Let's try that with rulers that measure length. So here you have a piece of wood, and you align the 0 with one edge of the length, and then you look at where the other end falls. And here the end of the object is between 4 and 5 centimeters. The ruler is in centimeters. So you know for sure it's between 4 and 5. So you can write already that it's 4 point, and then you need to estimate where the end of the object falls. And so what you do is you mentally divide the space between 4 and 5 into 10 equal spaces, and you estimate where is the object falling. So here it feels like it's right in the middle, so I would say 0.5 again. So I would report this measurement as 4.5, right? We know the 4 for sure, and the 0.5 is estimated. We estimated between the marks. If we look at this new ruler, it has much more lines, which means it's much more precise, because we will be able to give one more decimal, as you will see. This ruler is marked every 0.1 centimeters, because if you look from 0 to 1, it's divided into 10 equal spaces. And so between the 0 and the first mark that comes after the 0, it's 0.1 centimeter. And so, for example, right before the line for 1, that line before the 1 is 0.9 centimeters. So now if we look at our object, it falls between 4.5 and 4.6, right? The 4.5 is the slightly longer line, and then 4.6 is the shorter one after. So we know for sure it's 4.5, and we know it's not 4.6, it's smaller. So we can write 4.5 for sure. These are known for sure. And now we need to estimate the space between 4.5 and 4.6 and divide that into 10 equal pieces, and then estimate how many pieces we have from the 4.5 to the edge of the object. And here I would say 4.5, 6 or 7. Here it's reported as 4.55, which is also okay. Because it's an estimated digit, right? The last digit to the right is estimated, which means depending on the person who reads it, it will be different. And so I personally would read this as 4.56. Here it says on the slide 4.55, and it's still okay. Both are acceptable values. So sometimes the end of the object falls exactly on a line. And so you still need to estimate one more digit when this happens. And students tend to forget that. And so if we look at this object, we know it's looks like it's 3 centimeters exactly. But to say that it's 3 centimeters exactly, you have to say 0.0, 3.0, because this ruler allows you to read to 0.1, right? Because we have a line for 3 and then a line for 4 centimeters. But here, because it falls exactly on the line for 3, you have to estimate one more digit and say it's 0.0, right? It's not 3.1 or 2.9, it's 3.0 because it's exactly on the line. So try this. This is a learning check to make you practice this. And so please pause the video to work this on your own before you check the answer. This is the only way for you to learn, is to try for yourself. So what is the length of the red line? It's centimeters here. We have 8 centimeters, 9 centimeters, and then 10. We see that the red line is past 9 centimeters, but it's before the next line. So you can write that it's 9 for sure. And it's between 9.0 and 9.1, because the first line, black line that comes after your the end of your object is 9.1. So we know it's between 9.0 and 9.1, and we have to estimate one more digit. So we can write for sure it's 9.0. Sorry, yeah, we have to say that it's 9.0 for sure, but it's not yet 9.1. And so we have to estimate between 9.0 and 9.1. And here it's slightly before the middle of the space between 9.0 and 9.1. So you can say that it's 9.3 or 9.4. Both answers are correct, because again, the last digit is an estimated digit and it depends on the person who reads the measurement. And so it's okay if it's not the same digit for everybody. We say that the last digit is estimated and is uncertain. It carries the uncertainty of the measurement. And that's that digit to which you will add 1 and subtract 1 to get the range of values for which you are sure your measurement is included. Another try here, again, pause the video to try this. What's the liquid's volume in milliliters in this graduated cylinder? So this is a more tricky one, and actually I don't really expect you to know necessarily how to read this from what I told you about before, because here we have lines every 0.2. If you look, going from 3 to 4, you have 1, 2, 3, 4, 5 divisions, right? 5 spaces there. And so to go from 3.0 to 4.0, you actually go from 3.0 to 3.2, 3.4, 3.6, 3.8, and then 4.0. So the way to read those is not exactly the same. We don't divide the space into 10 equal spaces because here we have 0.2, it's not 0.1. So the way we would read that is we would read the number as long as it's between, and here it's between 3.4 and 3.6. So we know for sure it's between 3.4 and 3.6. And because it's in between, we would read it as 3.5. Oops. Okay, the volume is comprised between 3.4 and 3.6. The bottom of the meniscus is in between, so you would estimate this as 3.5. The 5 is estimated and carries the uncertainty. So these, when you have this kind of lines, remember that it's not exactly the same way to read it. You don't divide the space into 10 equal spaces, but you read the value that is in between and not marked with a line. So significant figures are the way that measurements show their precision. The more significant figures you have, and the more precise is your measurement. But first, let's look at what is an exact number. An exact number results from counting objects or is part of a definition. For example, if you count things that you cannot divide, like fingers and toes and chairs or tables, you cannot say I have a half table or a half finger. They have to be whole. So these would lead to exact numbers. These measurements are exact numbers. Another way that we encounter exact numbers is when we have those equalities from the metric system, especially. The metric system has been established to have exact values between units. And so by definition, a meter is exactly 100 centimeters. And so the 1 and the 100 are exact numbers, which means you could add 0.0 and many zeros and it would still be the same value. An inexact number is a result of a measurement or an observation and contains some uncertainty. We just saw how the estimated digit at the end of a measurement carries the uncertainty. And so when you have a measurement like that, you have an inexact number. For example, if you measure a length and it's 15.3 centimeters, so the 15 is known for certain, right? Because we read that there were lines to show us that it was 15 centimeters at least. And then the 0.3 is estimated, and somebody else could have said 0.4. And so that last digit to the right carries the uncertainty, and it's our last significant figure. So another example, 1,000.8 grams, it's a measurement of mass. Here, typically mass, you will see that it's given by a balance. And when you read a mass from a balance, you record all the decimals that the balance gives you. And so here the balance was precise to 1 decimal only after the dot. And so that 8 here to the right of the number is estimated. The balance, the last digit or the last decimal that the balance gives you is an estimated number, because often balance flickers with their last digit, and so that last digit is definitely estimated. That's another example of a measured number that would be an inexact number that would carry uncertainty in the last digit to the right. And here the 4 would be the uncertain number, the estimated one. So significant figures are a way to tell the others, you know, what is the precision of your measurement. And so we need to be able to count the number of significant figures in a measurement. And significant figures are all the digits in a measured number, including the estimated digit. And so all non-zero digits are always significant. And that should make sense because they have a value, right? 65.2 grams, for example, has 3 significant figures. The 6 is meaningful, the 5 is meaningful, the 2.2 is meaningful. Another example of 255.345 grams, this number would have 6 significant figures because all the digits are significant. So 3 to the left of the decimal point plus 3 to the right of the decimal point, that's 6 significant figures in that number. So non-zero digits always significant. Where it's not so easy, it's when you have zeros. And there are rules that you need to remember. And you will need to remember this all quarter long. We will pay attention to significant figures for the whole course. Whenever you continue with chemistry, you will be expected to remember this. So the first rule for a zero is that they count as a significant figure when it occurs between 2 non-zero digits. For example, 29.05 grams. In that number, the 0 is between non-zero digits. So when it's sandwiched by non-zero digits, those zeros count. Another example, 1.0087 milliliters. Here, everything counts. So you would have 1, 2, 3, 4, 5 significant figures in that measurement. The 0 count because they are between non-zero digits. The 0 count when they are at the end of a number with a decimal point. For example, 3.7500 centimeters. In this length, the 3 is known for certain, the 7, the 5, the first 0, and then the last 0 is estimated. And they all count because we see the decimal point here. The point between the dot between 3 and 7 here is visible. And so that makes all the zeros after the non-zero digit significant because we see the dot. So in this number, we would have 5 significant figures. In 620 pound, here we have 3 significant figures. All digits are significant, the 6, the 2, and the 0, because we see the decimal point. If the dot here was not shown, you will see in the next slide would be different. But when you see the dot, it indicates everything matters, everything is meaningful, everything is significant. So here we would have 3 significant figures. A 0 does not count as a significant figure when it occurs at the beginning of a number. So let's say we have 0.00245 milligrams. In that example, the first 3 zeros are not significant. They come before a non-zero digit, and so they do not count. They're only here to show you where is the decimal point, actually. It's what we call place holding zeros. They show you where is the dot. And until you see a non-zero digit, you do not start counting. So you count the 2, the 3, the 4, and the 5, and that's 3 significant figures in that number. In 0.008 milliliters, again, the zeros are not significant. They're only here to show you where is the dot. And until you reach a non-zero digit, so going from left to right until you reach a non-zero digit, those zeros do not count. So that number would only have one significant figures, and that would be the 8. Zeros at the end of a number that does not have a decimal point do not count. They are not significant. In this number 2570, all non-zero digits are significant. And then that zero, the last zero, is not significant because we do not see the decimal point. So it's not significant. And so that number has only 3 significant figures. If we were to see the dot, that would change everything because then the 0 would be significant. So be very mindful when you write your numbers. Don't just do a dot, you know, as a habit, for example. It's meaningful if you put the dot or if you do not put the dot. So be very mindful of that. Another example, 1,245,500 meters. So you start counting from the left. You have non-zero digits, they all count. And then you reach those zeros and there is no decimal point visible. So that means those zeros are not significant. And so in this number, we would only have 5 significant figures. So let's practice this. Yes, it needs a lot of practice. So please pause the video to try this on your own before you watch the answer. It is important that you try that by yourself before you watch the answer. So state the number of significant figures in each of the following measurements. 0.030 meters. In this number, so you want to start counting from the left, going from left to right. First, you have that first 0 and then the dot, and then another 0, and then a 3, and then a 0. Those first 2 zeros are called the leading zeros or place holding zeros. They do not count. They are only here to show you where is located where is the dot located. So those first 2 zeros to the left are not significant. Then you hit the 3 and that's a non-zero digit, so that counts. And after you've seen the 3, then whatever comes after will count. And so the 0 to the right of the 3 is significant. So in this measurement, we have 2 significant figures, and it's the 3 and the 0 to its right. 4.050 liters. So start from the left. The 4 is a non-zero digit, so it counts. Then you see a 0 and then a 5. All of these count. And then another 0. Because you saw a non-zero digit before the dot, everything will count after that. Because you see the dot, and it's a non-zero digit to the left of the dot, so everything will count. So the 4.050, they are all significant digits. And this measurement would have 4 significant figures. So make sure to understand that this 0 to the right is significant because we see the decimal point. In measurement C, 0.0008 grams. So starting from the left, we start with the 0 dot, then 0.008. All these zeros are not significant. They are only here to show you where is located the decimal point. And so they do not count, they are not significant until you reach the 8. And there's nothing after the 8, so that means it's only one significant figures in that measurement. Measurement D, 2.80 meters. Starting from the left, you have the 2, that's significant, the 0.8, it's significant, and then the 0. That 0 is significant because you have the dot visible, and it's to the right, and so it's meaningful. So in that number, you would have 3 significant figures. 1,200 meters. The 1 is significant, the 2 is significant, and then the 2 zeros that come after that are not significant. They're not significant because you do not see the decimal point anywhere. It's not shown, and that's on purpose. So if you do not see the decimal point, those 2 zeros to the right of the 2 are not significant. And so that measurement has only 2 significant figures. Now measurement E, 500 grams. Here the 5 is significant, and then there's 2 zeros and the decimal point. Because you see the decimal point here, it makes those 2 zeros significant. So that number would have 3 significant figures. So I hope this is clear that when you see like between measurement F and E, if 1,200 had a dot at the end, it would be 4 significant figures. Because it has no dots, then it's 2 significant figures. Same thing with the 500 here. Because we see the decimal point, it has 3 significant figures. But if you didn't show the decimal point, then it would be 1 significant figure. With practice, it will come, but it requires practice. It requires that you are trying on your own and not just following along. You really need to think about it yourself, and will come with practice. Some more practice. Which answer contains 3 significant figures? Again, please pause the video and think about this before watching the answer. So first question A, which answer contains 3 significant figures? Here there is only one solution, and that solution is number 2. In that number, if you look, starting from the left, you can't, you do not count those zeros. Those zeros are not significant. Those zeros to the left, they only show you where is the decimal point. They have no other function than that. And then you start counting significant figures from the 4, 7, and 6. So that's 3 significant figures. In the first choice, 0.4760, the first 0 is not significant. And then you would start counting from the 4. Going to the right. So the 4 is significant, the 7, the 6, and the 0. So here it would be 4 significant figures in answer 1. And in answer 3, this is a number in scientific notation. We will learn about scientific notation after this. And when you have a number in scientific notation, everything counts in the decimal part. The times 10 to the 3rd power here doesn't matter for counting number of significant figures. The times 10 to the 3rd is the exponential part of the scientific notation, and we do not use it to count the number of significant figures. So in 4.076 here in the decimal part, there is 4 significant figures. Question B, all the zeros are significant in... And so here there is 2 answers, 2 answers. So first answer, 25.300. all the zeros are significant in that number because you see the decimal point and you have non-zero digits before the zeros come in. So that makes those zero at the end to the right, they are significant. So we have 5 significant figures in that answer too. In answer 3, all the zeros are significant too, because if you look at the number starting from the left, we have 2.050. We have a dot and we have a non-zero digit before the zero come in. So then that makes those zeros significant because we see the decimal point and we have a non-zero digit in front of it. So the 0 between the 2 and the 5 is, always significant because it's between non-zero digit. And the 0 after the 5 is also significant because we see the decimal point. So everything counts. In answer 1, going from the left to the right, you start with a 0.00307. Those first 3 zeros to the left are not significant. And you start counting from the 3. And then you count that 0 and then the 7. So only 307 here are significant. And so that would be 3 significant figures in that number. The number of significant figures in 5.80 times 10 to the second power is, so 1, 2, or 3? And the answer is 3, because the 0 is significant. When you have 5.80, the 0 comes after the decimal point and it comes after non-zero digits. So it is meaningful, it is significant. So we have 3 significant figures in that number.